Okay, so let's start talking about this first chapter of the course. This is actually the second chapter of the book, but it is the first chapter that will consist of entirely new content in this class for us. So you're responsible for reading everything that you need from chapter 1 and from completing all assignments that require you to do that. And after this, we're going to start actually getting our hands dirty with calculus. So let's get that done first. First, I thought I'd go over some of the interesting things on page 1 here, which is a preview of calculus. You can find some interesting information about the course and about this area of mathematics in that page. This is the first thing that caught my attention. It says that by the time you finish this course, you'll be able to calculate the length of the curve used to design the Gateway Arch in St. Louis. If you don't know, that is this curve over here, this monument in St. Louis. You'll be able to determine where a pilot should start descent for a smooth landing, and this is one of the projects that I intend to use and to assign during this class. How to compute the force on a baseball bat when it strikes the ball. So how do you figure out what's the force, right? How do you figure out where it goes, how far it goes, and measure the amount of light sensed by the human eye as the pupil changes size. So all of these many applications, they require some very, very advanced mathematical tools. And we're going to start talking about the most basic of them today, which is limits. So let's first talk about some classical problems that people have struggled with, mathematicians have struggled with over the years. So this here is first talking to you about the area problem. And this is something that the ancient Greeks did struggle with and were very curious about. And it basically consists of, given any shape, how can you calculate the area of that shape? You can start with a circle. Right, here's a circle. Now we know that the formula for the area of a circle is pi r squared. But how do you think that the ancient Greek came up with this formula, or even if they did know, right? How they even find pi and where did it come from at all, right? So the idea that they had is what they call the method of exhaustion. So the method of exhaustion is a way to calculate areas by just dividing whatever shape that you have into triangles. So if you have like any weird looking polygon like this, even if it's not regular like that one, you can sort of pick a point and start cutting it into triangles, right? And hopefully, if you remember your math 142, you're able to find the area of each triangle, and then you add all areas up, you get the area of your weird shape. What about your circle, right? If you try and do that with a circle, you're not going to get triangles, because if you try and do that, this side here is not a straight line, right? It's like a curved arc of a circumference. So you can't do that. So here's what the ancient Greek thought about. Actually, this is an idea that came much later. This is a problem the Greek struggled with, but this idea of considering polygons that I'll talk about now came much later. So what you do is imagine that you have a triangle inscribed in your circle. So your triangle. You know how to calculate this area. It's not that close to the area of a circle, but it's a start, right? You know this much here is missing, right? From, it's the difference between the area of your circle and the area of your triangle. If you do a square instead, right? And you can call it A4, the area of the square. The difference, you can see that it is smaller, right? You're much closer to the area of the circle than you were before. You call the area of this square here A4. You can do the same thing with a pentagon, right? So make it 5 sides. Call the area of this guy A5. And the difference is here. It's much smaller than it was before, so you're not quite there yet. And call this area A5. Right? So you keep doing that, adding one side. So got a hexagon, a heptagon, and an octagon, and then you can keep going. And the further you go, the closer the area of your polygon gets to the actual area of the circle. Okay, so this is the main idea here in this process. The further you go, the closer you get to the actual answer, which is what you're looking for. This is the idea of a limit, right? The area that you're looking for, A, the area of the circle. So this is going to be the area of the circle for me. It is the limit, and this notation may not make sense to you right now, and it's fine. I just want you to understand the intuition of it. It is the limit of an, right, as n gets large. So as, we keep repeating, add more and more sides to our polygon, we get closer and closer to the actual answer, which is the area of the circle. Okay, so this is very crucial, very interesting idea that took many, many centuries to get developed fully, and we're gonna use this idea in this course. So this specifically here is gonna be the focus of math 152. We call it integral calculus. When you calculate areas, this is integral calculus. Use the size of my marker here. Okay, so just the takeaway here should be the idea. The more sides you add to your polygon that is inscribed, the closer the area gets to the actual answer, and you were able to calculate each of those, so you're able to sort of iterate this process. And this is a limit. This is a problem that we will solve in this class, so we are going to talk about the tangent problem first. So consider the problem trying to find an equation for the tangent line to a curve. We're going to talk about more precisely what a tangent is. Tangent, intuitively for now, is just going to be a line that sort of touches the graph at one point and just doesn't touch it again. It could happen that it touches it again, like if it does something like this, the graph. But it does not matter for this point. You're talking about local, touches at a single point locally. If it touches again, it's got to be far away. That's the idea, right? So first of all, how can we ever calculate the slope of this line? And that's the first issue, right? We have a point. To find the equation of this line, we need a slope. So I call it, what's m? I want to know the slope, right? Keep my notes open here so I don't lose track of what I'm doing. Okay, we're looking for the slope, and that's our question. Let me make it red. What's the slope of that line? Because we already have a point. If we find the slope, we have the equation of the line. Okay, here's the answer. We don't. We start with a line that's close to that line, or not even necessarily that. Start with this line, say. Let's say this is point Q, right? And if I want, I can draw a line through P and Q. This I know how to do because I know 2 points, right? When I have 2 points, I know how to draw a line through these 2 points. And if I want to know the slope of this is called the secant line, right? This is called the secant line. This is called the secant line, and this is a tangent line. So this is the secant line at P and Q. We know how to calculate the slope of this, and the slope is going to be, let me just write a few more things. Determined by these two guys. Let me call MQ the slope of the secant line at P and Q. So say the line is secant at P and Q because it touches these 2 points. It's determined by these 2 points. Any 2 points determine a line, right? So you can find like a point slope or any other type of equation for that line. So we know the equation of that line. We know that slope. But what does that have to do with the red one, which is what I want, right? What does that have to do with this? Well, I can, if I want, pick Q that's closer to this. So if I call this Q1, I could pick another Q here, say Q2, and let me make it green. And I'm picking this like randomly. Not going to do any math on this. But I'm just trying to explain what the thought process is, right? So you pick like another Q. You can see that the green one is a little bit closer to the red one. Still not quite that close, but you can still pick another if you want to make it better. So if I pick, let's say purple, let's make Q over here, Q3. And when you draw the line through P and Q2, now I have a purple line that's a lot closer to the red one. Okay, so that's the idea. So pick Q as close as P as you want to get MQ as close to P, right? As close to P, as close to M as you want. So the closer you choose Q to P, the closer the slope of the secant line is to the slope of the tangent line. And that's the idea of how you solve the tangent problem. This is something people struggled with for a very, very long time. It got solved, I think, about the 1700s, around the 1700s, by Newton, Leibniz. We're gonna talk about these people as the class progresses. Take a second, stop here, try and understand what I'm trying to say. If you don't understand it fully, that's fine. We're gonna get there as time goes on. Below is a more detailed, a better drawn picture. This is from the book. Okay, so you can see here, that this green triangle that they drew is this slope here, right? Is what you use to calculate the slope. So it's f of x minus f of a is the height of that triangle. X minus a is the base of that triangle, and f of x minus f of a over x minus a will be mq. It's the slope of this blue line. Okay, and look at this notation again. First time, if it's the first time you're seeing this, it may not make sense, but try and understand what I'm trying to say, and try and see sort of the hints in this notation that tell you what I'm saying. So okay, MQ is the slope, is this thing here that I just wrote, right? The limit is this idea that I'm trying to make, Q as close to P as I can, and this is what's telling me, this Q with an arrow pointing to P is what's telling me this, right? I'm calculating the limit of MPQ, so they call it MPQ instead of MQ, so let me change that, right? MPQ, and let me change that in the previous page as well. But that's the idea. MPQ is something that you know how to calculate, but you need 2 points for it, when in reality you only have one, so you make the second point as close to the first as you can, and that way your blue line or your MPQ is as close to what you want as you need, right? So if it's not close enough, you just make Q closer to P, and that's the idea of limit. Okay, so this is just like warming you up to the idea of what limits can do and what derivatives are. This is a derivative for us. It will be. So if you recognize this from 141 and 142, this is what we call the quotient difference. If you want to review this, you can. We're going to do this many, many times throughout this quarter. We're going to actually calculate some of these things. Okay, so done with the preview. with what we're trying to do and what the ideas of the course are, let's talk about the tangent problem and the velocity problem with a little bit more detail. Let's do some math. I have my calculator here on me. If you want to have yours, you can. So let's talk about the tangent problem again with a little bit more detail. So like I said before, the word tangent is derived from tangens, which means touching, right? So basically a tangent is a line that touches the curve. This is very loose wording. We're going to formalize this idea further after we define everything that we need to define. But right now, you should just follow this intuitive idea, which is what the Greek had and the people who created calculus had in mind too. We're looking for a line that sort of touches the curve, whichever curve you want, sort of following the same direction as the curve, okay? Another way that you can think about this, for example, imagine that you're driving, right? Imagine this is like a road and you're driving. And let's say I'm driving on that road. And eventually on that point, I decide to stop, to sort of turn the wheel like straight, right? Make it straight and just follow this direction. This direction that I'm going in, right, is the tangent line. If in the middle of the curve, I just decide to make the wheel straight and keep going forward, this is the tangent line, okay? So just so you have an idea. But we're going to formalize this further using limits. So limits, again, the first main idea of the class. Okay, keep going. So let's talk about the velocity problem, because this is a problem that will hint towards limits. Let's talk about this. So let's suppose that a ball is dropped from the upper observation deck at the Space Needle Seattle. Let's say that this is 605 feet above the ground, and let's try and find the velocity of the ball for 5 seconds. I've never been to the Space Needle. I don't know if this is accurate to how the Space Needle's format is. I'm just trying to use something that's close to us. But let's say that you drop a ball from the Space Needle. This is the height, 605 feet. We want to know the velocity after 5 seconds. So first of all, from the wording, find the velocity after 5 seconds. From the wording, we don't want to know the velocity, the average velocity during these 5 seconds. We'll know the velocity at 5 seconds. Okay? Take a second to understand how these two things are different. Now, let me maybe exemplify this. As soon as I drop the ball, this is t equals 0, right? Maybe a second later, ball's over here. Maybe 2 seconds later, as the ball is dropping, it's falling, it's gaining velocity, it's gaining speed. So, because it went a little bit faster, maybe this is t equals 2, right? You see the distance is bigger, and then you can say this is t equals 3, and maybe, as it gains speed, this is t equals to 5, very close to falling. Okay, so what I'm trying to say is each of those intervals, let me make it a bit further, is bigger than the previous one. Okay? So I do not want to know the average velocity, meaning between t equals 0 and t equals 5. I want to know the exact velocity at t equals 5. Okay? Another way, if you want to think about cars and driving again, you can think about it in terms of, if instead of a ball you were talking about a car driving on a highway, you want to know the exact reading of the speedometer of the car, right? The little needle that some cars have, most cars have, showing the speed of the car, right? You want to know the exact reading of that on the ball that's dropping, okay? So, like I said before the difficulty is that we're dealing with a single instant of time, t equals 5 seconds, and no interval. So we don't have an interval to use. And that's the huge difficulty that we have and that we're going to overcome in this quarter. Okay, so we're going to talk about instants of time rather than intervals of time. So we're going to use some classical physics here, some mechanics. So this is Galileo, Italian scientist, very intelligent person, very many discoveries, publicized by him. And he gives us the distance. So all that he does is the distance. So what Galileo gives us is, so for example, this here would be s of 1. Okay? Maybe use it red again so you can see better. This distance between these two, this is s of 1. Difference between t equals 0, t equals 1. This distance here is s of 2. You know, this whole distance here, s of 3. Okay? And this whole is s of 5. So this formula gives us this. But we don't want to know this. Again, we want to know the velocity. So we're going to use the formulas for average velocity to sort of try and hint at this idea of limit using this problem. So let's go. So let's do this. Let's talk about certain time intervals. Let's guess. Let's try and think, you know, what happens between 5 and 6, for example. T between 5 and 6. So what's velocity here? So let's see what we can do with that. Make a table. I just chose 5 and 6. Could have chosen 5 and 4 if I wanted. I could have chosen 4.5 and 5.5 because what I'm doing is I'm trying to get closer and closer, very small interval, very close to 5. Okay, this is what I'm trying to do, following the ideas from before. So what's the average velocity here? So let's find what's s of 5. So s of 5 from Galileo's formula. That is the distance the ball travels, 0 to 5, which is 4.9 times 5 squared. And that's why I have my calculator here, so I'll just do that. Start it on. So 4.9 times 5 squared. And that's 122.5. Let's find s of 6 because I'm trying to find the average velocity. Right? Let me even rewrite this as average velocity. This way you know what I'm doing. So it's 4.9 times 5 squared. Sorry, times 6 squared because that's s of 6. So that will be 9 times 36, so that's 176.4. So our average velocity, if you remember from physics, right, that's the distance traveled, and usually use s instead, like space over time. So that will be, you know, the difference between these two. That's the velocity, the distance traveled. So it's s of 6 minus s of 5 divided by 6 minus 5, right? The interval of time, the variation of space divided by the variation in time. So 176.4 minus 122.5 over 6 minus 5 is 1. So I just do this. 122.5. So that's 53.9. That's 53.9 feet per second. So okay, so I have an average velocity, you know, between 5 and 6 seconds. But that's not what I want. I want exactly at 5 seconds. What can I do? I can make my interval smaller. So what if I do, you know, 5? What if I do 5 to very close to 5.1 seconds, right? So I'm doing 5 seconds to 5.1 seconds. Right, so I find s of 5.1. So let me call this, let me label these guys so that we don't lose ourselves. It's going to be 1. Call this 1. It's going to be my second calculation. So when I get there, I'll tell you. So s of 5.1 by following Galileo's formula from the previous slide again, right? 4.9 times 5.1 squared. So it's going to be a little bit tedious until you understand, right? 4.9 times 5.1 squared. So that's going to be a 127.449. So I'll do, the number 2 that I'm calculating the average velocity here. It will be S of 5.1 minus S of 5, right? Variation in distance, divided by the variation in time, so 5.1 minus 5. You get what I'm doing, right? Don't have to follow every single detail along if you know what I'm doing. So this is 127.449 minus 122.5. That's divided by 0.1, right? So I'll do that math. Minus 122.5. That's divided by 0.1. And that's 49.49. 49 I'll say 49, I'll leave it like that. 49.49. So, following the idea that I had at the beginning of the sort of choosing point P, Q, closer and closer to point P, now that I've chosen an interval very, very close to 5, right? This would be like my point Q here, right? The second point. The closer I get to 5, the closer this answer here is to what I'm looking for. Okay? I'll do one more time, and then I'll stop so that you understand what I'm trying to do. If you already understand, feel free to skip this and go to the following page, which is where I end the slideshow. But I'll just do it one more time in case you need to understand what I'm doing. Okay, so let me do number 3 right here. So let me do this. So now let's go very, very small interval. Let's say t is between, 5 seconds and let's say 5.05 seconds. Okay, so 5.05 is closer than 5.1. So I need to find S of 5.05, and that's 4.9 times 5.05 squared. 4.9 times 5.05 squared. And that's 124.96225. And then I go V equal to, S of 5.05 minus, S of, that's right. S of 5 divided by 5.05 minus 5. We'll go ahead and add a page here so that we can follow along better and have more space. So this will be continuing. So this will be 124.96225 minus 122.5 divided by 0.05. I'll use my calculator for that. So minus 122.5 divided by 0.05, and that's 49.245. It's 49.245. Look how small the variation was. Feet per second. Look how small my variation was. I could say if that were like a real issue that I was trying to determine, a real problem that I was trying to solve in real life, I could say, hey, it changed so little from one approximation to the next that maybe I should stop here, and this is a very fair approximation. I could say, you know what, maybe 49 is where this is going. Or maybe I could try a few more. I recommend that you try a few more on your own just to make sure that you know what's going on, and then you compare your answers to what you see in this following slide over there. You can see that we're getting very, very close to 49, okay? This is the idea of limit. And you can read this, because I would say that this is an idea that we're going to use over and over in this class and in the following one. As the interval gets smaller, right, the interval gets smaller and smaller, the average velocity gets closer and closer to 49. Let me correct this because this is meters and this is supposed to be feet per second. Okay? Let me do this. Let me just cross this out. So feet per second. Okay, so this is the idea. Do a few on your own, just as practice. We're going to explore this idea further throughout this class, like I said before. But this is how these things work. You're trying to make a certain point closer and closer to another, and then a certain value that you use these points for get closer and closer to an answer that you're looking for. Okay, this is what this is. This is what calculus is about. This is the velocity problem. I'll stop here. Thank you for watching.